Uh, Rahul, Kavita, and Ravi has joined. So you can ask if you have any doubt or any clarification you need about the course. You can ask, preferably in chat, or if you want, you can also ask by unmuting on mic and question. Okay, so I'll be happy to answer any doubt you have. So you have any questions, you can chat, keep your question in the chat box, or you can ask me directly as well because the number of people is less. Okay, so which type of model check are we use when design VLSI chip? So you are talking about uh, verification, right? Model checking by property checking, right? I guess that is your question. So it depends on in industry they have their commercial product, but in academics we usually use NUSMB, which is a very popular model checker. But in the industry they also use this kind of tool in the backend, but they have their own commercial product. And if you look into this companies like Synopsys Cadence, so they have their own product, right? So which they sell and VLSI industry use them. So you want to name me certain few tool, right? So uh, you can just Google it, right? So then Cadence formal verification tool, you can just search, or formal verification product from Synopsys. You will get those answers, right? So for me, let's say if I just search here. So this Jasper Gold is one of the product from Cadence. Similarly, if you just search for with Synopsys, right? So VC formal, right? So these are the product it's getting in industry, right? So, uh, but in academics, for example, for our in my group, whatever research we do, whenever we need model checker, we usually use new assembly. Uh, I think that answer your question, right? So to answer your yeah, NewSMB is a very good tool I have used in my research as well, and my student also use it. And commercial product like Jasper Gold from Cadence or from Synopsys, you have tool like VC Formal. So these are from commercial tool, and in academics we are very much familiar with new assembly. Spin is also there, but I never use it. So for new assembly, I have used quite few in my work. Okay. Kavita has a question. Good afternoon. Yes, good afternoon, Kavita. Uh, yes, so I would like to know some textbooks or material that we can use for this course. Yeah, it's a good question. So I have already mentioned in the last live classes also. I'll just copy paste the same thing here as well. So there are the theory part, whatever I cover, usually I cover from uh, that D. Michelis book. So that is a really great book. I'll just copy paste the book reference here. You will get it. And the book is, I think, soft copy is also available. You can just Google it and you'll get it. Okay. So I'll just copy paste the book name. So this is a very good book for the theory, the scheduling part, allocation, binding, those part. This book is really great. Okay. And for the latter part, I recommend this book. This I found is really interesting. Is this book? Again, this book soft copy is available. It's basically parallel programming for FPGA. It's a soft copy available. In this book, the best part is that uh, this book also I'll recommend all the students to follow. This book is the best part of the second book, the Karstner book. It's basically have taken it's exactly the way I taught the second part of the course. Okay. In the sense, I mentioned many times in the course that you just write any C code, you don't get synthesis into efficient hardware, right? And if you just apply HLS, you may not get efficient hardware. So what you have to do, you have to rewrite your code or manually modify your code to make it hardware friendly. Similarly, you need to understand the HLS optimization availability and which fits where, right? It's not that you blindly apply certain optimization and it will work, right? You have to understand the context of those optimizations and where to apply. So what this second book does is take at least 10 examples and those they just synthesize the basic stuff and so what is the kind of timing or area you are getting. And then what they does is they optimize the design the way I just exactly told you that you modify the input behavior a little bit uh, to reduce the memory access and all those things. And then also they apply the optimization judiciously and then so that how you finally get a version of the code which is really uh, from which you can really generate an efficient hardware through HLS, right? So this two book is a very good reference for my course. And in fact, I do teach this course here in IIT Guwahati in the regular students here, and I recommend this to book for them. Okay. And if you want to learn about the optimizations available in the high level synthesis tool, I'll recommend you just go Vivato HLS design manual, right? So there, the detail of the optimizations, what is the optimizations, how they are going to be applied, where they are going to be applied, those details are given in the Vivato HLS design manual. Again, that is freely available. You can just download and go through it. So that's three things is sufficient, right? So maybe I'll just Google search and I'll put it here also for your Vivato. So yeah, so I'll just give one version, but there may be some user guide basically. Okay, so this is one of the older version I get, but you will get latest version if you Google it. Okay, so these three is the kind of enough for the course. First one is for the hardcore theory. Second one is for understanding how to apply optimization, and third is the list of optimization and what are the things available and how to use this. Okay. Okay, so I think I have answered Kavita's question. Uh, okay, any other questions? So if you have any questions, those who are joined late, you can always ask me questions directly here, or you can just ask your question in the chat. Okay, so I'll try to answer your questions or any doubt you have in my course. Or you can also give me any general feedback you have, say, if you feel something can be incorporated in the future version of the course or anything, whatever you have in your mind. Feel free to ask questions in the live session. It's basically for you. Uh, and if you do not have much questions, I'll end this live session soon. Okay. So I'll wait for your questions. So somebody is asking, what do you mean by C-based VLSI? I think if you're attending the course and the lecture one, you got your the answer of your questions, right? Uh, it looks like you have not attended the videos of my course, right? Anyway, if you ask question, I'll answer. It's basically VLSI design is what you want to design a chip, right? And usually people start writing RTL, register transfer level design, in Verilog, VHDL, or any other description language. From there, they synthesize the design, right? And then they get the layout, and then they fabricate and they get the IC. What this course is about is make the whole process one level up, right? In the sense, instead of starting the whole process from RTL, can I take my specification written in C and I can convert it automatically into RTL, right? So that's the course all about. And this course talks about all the background theories, all the optimizations, everything related to this C-based VLSI design, in the sense that you have a C specification and you want to get a chip out of it, right? So that's the C-based VLSI design. If you have any questions, you can always feel free to ask me in this chat box. Okay, so I don't know the question of this Saurabh Kumar anyway. So I think so. Kavita as ASCII, this course is more interesting. Please suggest, give some overview about many projects based on this course. Okay, it's a good suggestion, Kavita. So what I did in my course here is we take certain applications. You take an image processing application, for example. Okay, and you basically take any image processing books. You take an image processing application like say filter or say edge detection. There are many, right? Noise cancellation. You take one of the application and you write the C code. Many of the time you'll get the C code from from the internet as well, or even from the book. And then you synthesize. You get what hardware you're getting, right? So you will basically see what hardware is you got from this basic specification without applying any optimization. Okay, and then you try to apply all the optimizations. And image processing is a very good domain because there are a lot of competition happen, and HLS should able to do can generate an efficient hardware. And most importantly, in the image processing piece, because you have a lot of array access, memory access, and there are lot of loops. So there is a lot of scope of application of this optimization like loop pipelining, loop unrolling, or say the optimization like this array partitioning, whatever I'm teaching in the class, right? So this can be a good exercise, and that's what I did in the course. And you can take also any cryptographic algorithm like AES. You Google search, you'll get a lot of resource, right? AES, DS, this kind of any application you can take, and you can take this as a challenge that and you can actually create many version of the RTL in the sense that some may be area optimized, some may be latency optimized, some may be timing optimized, right? And you will learn a lot of things in the sense that uh, to apply to improve the timing, probably certain optimization is very important. To improve the area, probably certain optimization is important, right? Or to improve the latency, you have to apply certain optimization techniques. So once you try to take an example and you try to optimize, you will learn a lot of things. So I think that can be a good practice for you. And this is what I did in my course here as well, that 1 year I've given all the image processing application, almost 20 applications as a course project, and people have shown that how they have optimized. Next year I've given cryptographic algorithms. There is one more good resource I can tell you that will be big project, not mini project. is that PQC, post-quantum cryptography. You have probably heard that now this standardization for the post-quantum cryptography is going on, and that is called PQC. If you just Google it, you'll get it. And from 64 application, now only 4 remaining, right? And those specifications given in C. And that can be, and it's a big code. It's not a small C code like 10 line, 15 lines, right? So you can take those C code, and once you try to, and you can synthesize them through HLS and can create harder out of it. And that can be really interesting job, I can tell you. And that can give you lot of things you learn through HLS as well. First, because of that, this is a very new thing. There is no solution exist in the market because these are only 4. One of them will become the standard for PQC. And if you can generate a hardware, that will be a new research idea as well, that you get on some hardware of that PQC implementation through HLS. And I can guarantee that you'll learn a lot of things, and you will become a master of HLS if we just take one of them and try to synthesize. Okay. So this can be a good big project, not mini project. Josna has a question. Good evening, sir. Yes, good afternoon. Will you update? Will you please differentiate iterative execution, partial loop unroll, and full loop unroll and loop pipeline? Yeah, I'll do that. So iterative execution means that suppose you have a loop, right? If the loop is say 10 iterations, the loop run from I equal to 1 to 10. And what you do is you basically find out how many time step you need to execute the loop, right? So the one iteration of the loop. And then maybe the loop body, there may be 10 operations, right? And you decide the schedule of 4 time step, that you can schedule those 10 operations in the loop in 4 time step. So one iteration of the execution will take 4 time step, then in 4 clock cycle. And now you are iteratively executing the loop in the sense now 4, and I have given an example, the loop have 10 iterations. So 4 into 10, it is basically 40 iterations it will take. And you need minimum resource for this because it's take more time. And you remember you want to develop a faster design that take less time, it will take more area, right? Sorry, in the sense, yeah. So if it is take less time, that is very faster, area will be more, right? And if the area is minimum, it will take more time to execute because the total number of computation is same, right? Whether you want to get the result in quick time or less, if you want to get it in less time, you have to compute the same number of operation in less time. So you need more resource, right? So the iterative thing, as I mentioned, that if the one iteration of the loop takes say 4 clock cycles and the loop has 10 iteration, it will take 4 into 10, 40 iterations, that means 40 clock cycles to execute the loop. But you need minimum resource because you need only the resource for one iteration of the loop, and that will be determined by the HLS. Okay. Then you just think about the completely unroll first. Okay. What is unroll? So basically you have one iteration. I have given 10 operations are there. So now you have 10 operations. And if you think about the all 10 iterations of the loop, there are 10 into 10, 100 operations are there, right? And you just think at simple example, AI equal to BI plus CI. It's happening in a loop, right? So that means, and the loop is running from 0 to 9. Okay. So that means you have A0 equal to B0 plus C0, A1 equal to B1 plus C1, A2 equal to B2 plus C2, and so on till A9 equal to B9 plus C9, right? So these are the operations you have. So this is 10 operations if you unroll. So what unroll does is basically remove the loop and put all the operations together. So now you have 100 operations, and now you apply your scheduling strategy. It may be that because there are 100 operations and there may be some operations of the 2 different iterations is not data dependent, we can execute them in parallel. So now scheduling happen for this 100 operations, not for 10 operations, right? So now this scheduler might schedule this all 100 operations in say 20 cycles. Now the loop will execute in 20 cycle and it will give you the results. So earlier in iterative, it is 4 into 10, 40 cycles. In unroll, you are getting in 20 cycles. So the unroll is basically you're removing the loop and you're exactly specifically right all the operation that can execute in all iterations of the loop, right? And then you apply normal scheduling strategy and whatever time you get. You see here, now you are taking 20 cycles, but definitely your resource will be more because there will be many parallel operations, which was not possible in one iteration. In one iteration, there are only 10 operations. Now you have 100 operations. There may be many operations can be parallel and they can be scheduled in the same time step. So unroll, although reduce the time to execute the loop, it will increase your resources, right? Then I'll talk about the partial unroll. Partial unroll is what? Suppose you have 10 iterations and every iteration has 10 operations. So there are total 100 operations altogether. If you completely unroll, there are 100 operations and there are too many resources you need to execute them, right? And complete iterative version, you have effectively 10 operations and you have to do scheduling for 10 operations and then you're going to use the same resource for all iterations, right? That is the minimum number of resource, maximum time, unroll, maximum number of resource, minimum time. And then partial is basically, I'm not going to completely unroll, right? So let's say I want to unroll by 2. That means whatever is happening in 2 iterations, that is going to happen in 1 iteration. So effectively loop earlier iterates for 10 iterations. Now it will iterate for 5 iterations because I want to unroll by 2. And in 1 iterations, operations of earlier loop 2 iterations will happen, right? If I give that AI equal to BI example, BI plus CI. So earlier the loop was I equal to 0 to 9 and AI equal to BI plus CI. What I'm going to do it now? I'll run the loop from 0 to 5 and I'll do AI equal to BI plus CI and AI plus 1 equal to BI plus 1 plus CI plus 1. So that means 2 operations I'm putting into one loop, but the number of iterations of the loop become by half. Okay? That's the unroll. So now it's basically a trade-off between the completely unroll versus iterative because it both has positive and negative as I mentioned, right? And then for that 2 iterations body you schedule and then you run for 5 iterations, right? So it's basically balancing between these two extreme. Okay. And the last thing is basically the loop pipelining, which is the best thing it can happen for loop. It's basically you decide how many iteration is taken. For example, the first example I've given, right? So it's probably say take 4 iterations to execute, but I'm not going to share any resource among the 4 steps. Okay. Instead, I'm going to put a pipeline stages between the stages. Okay. Now what is going to happen? Your first iteration data come, it will execute in the first stage. Next clock, second iteration data came and first iteration data go to the second stage. First iteration is executing on the data of the second iteration. In the third clock, third iteration data came. So that will be execute the first stage. Second iteration data is in the second stage and first iteration data in the third stage, right? So this way, the pipeline stages will happen and every iteration, new data will come and but different stage of the pipeline will execute different data, right? It will work on the different data. And what will happen here after when the pipeline stages are full, after every clock, you're going to get a new output of the next iteration, right? So what is going to happen here? You are not using as many as resource like your unrolling, or you are not using as less as resource as your completely iterative. You have pipeline stages where the stages won't share the resource most of the time if your initiation interval is 1, and then every iteration, one of the iteration will be over, right? Although one iteration is taking 4 clock, but you are going to get output in every clock, right? So this is the best thing. So loop pipelining is the best optimization that you can apply to get the output. Okay, I think this answer your questions, and please feel you attend the lecture where I have given the similar things in with examples. And if it is not clear, just I can elaborate more. You let me know. Okay. Mini project based on mechanical engineering, sort of. So to be honest, I'm not expert in mechanical engineering, but if you have certain application in mechanical engineering which you can write in C, you can always use high level synthesis to generate hardware. And that hardware can be utilized for a faster execution of that particular model, right? So if any mechanical engineering applications can be written in C, C++, you can use always high level synthesis to synthesize them into hardware. Okay. What is the research area in VLSI? Okay, Robbie was asking very. Anyway, I'll not go into detail. So in research area in VLSI, it depends on your interest. The way I work, I also work on the VLSI area, but I work in formal verification in the sense how you can formally verify certain design you are getting synthesized through these tools. I'm also working on this high level synthesis and efficient synthesis of uh, hardware, hardware from a C specification, and also the security aspect in this, right? So that I have already covered in the courses as well, that you design certain, you get a VLSI chip through high level synthesis, but it may be not secure from IP piracy and overbuilding. So can you develop a chip through HLS which is secure from IP piracy, right? This is another area where I work on. And also I work on hardware security. So hardware security is another big concern. So for example, you think about AES algorithm, cryptic algorithms, right? So they are basically secure theoretically. But when you apply, when you try to implement them in hardware, because of many side channels like power, timing, uh, it may leak information, and you can actually hack a AES algorithm once it is implemented in hardware, and you have not taken proper care of the information leakage, right? So this is another very good area of research where people try to develop hardware for and cryptographic algorithm to prevent any side channels, right? This is a very active area of research. Post-quantum cryptography is another area where people are working on generating hardware for that, creating standard for that. Approximation computing is something another area. Say, for example, you have a very large cryptographic algorithm. It if you want to execute in IoT devices, which has very less power, right? So it consume a lot of battery power. So can I have an lightweight version of that, right? So similarly, think about approximate multiplier, approximate adder, those things, right? So approximation computing is another area where people will do a lot of research. So I have already mentioned 7, 8. You can just take one of them as your research area, Ravi. Please ask Hindi. I don't understand English. I'm sorry. I think English is the standard medium here. If you do not, please, I can't help, to be honest. So Pratik Ognihantri asks, please send link at some Gmail ID, right? I think there are live session will be recorded, and if you attend it, it will the video of this will be available here itself. Okay, so I remember in the last live session video was available in the same chat box, right? If you come back, you will see that video is available. Um, so Jyotsna mentioned some appreciation here that this is pleasing you to provide solution for the completed assignments as well as for future assignments. Yeah. So yeah, if you need solution, please just email us on that forum. We'll always give you, because whenever we have the problem, we have the solution as well. Uh, so you can always, if you need any solution, I think TAs are giving that. If you need, you can always put your queries. We'll always give the solution. Okay. Thank you. Pratik mentioned that how do data allocation binding using a Xilinx? Yeah, so it is already internal to the tool, right? You don't have to bother about anything. But it basically you can guide the tool to do that, right? For example, if you apply loop pipeline in the example that I've given here, it automatically do not share resource among the pipeline stages, right? But if you do not specify that you apply loop pipelining, it will automatically implement the iterative version, and it is going to share the resource among the iterations, right? Because that is what this allocation and binding works. So as long as when you are basically using this tool, you don't have to apply, you don't need to think about this allocation and binding or scheduling. Everything is done by the tool itself. One thing you have to understand very well, that how to control that, right? How to make sure that you have a pipeline version rather than iterative version, and how the allocation works for a pipeline version compared to the iterative version. So that's something you need to understand. I think Pratik has some more questions. So which case code best suite for synthesis of C code? I don't understand your question, Pratik. You can switch on your mic and tell me because okay. Which case code based
Hello.
suite? I don't know. Yeah. Pratik, you tell me. What's your question? I don't
Yeah,
understand.
I am asking. So I am sir. What is the sir? Basically, efficient synthesization of any C code using a VLSI. Efficient utilization means which tool particular for industry support will be used, like as Mentor Graphics, Intel's, or as
Okay,
well as
okay.
Synopsys.
Understood. Thank you. Yeah. So to answer your questions, if you want to generate for FPGA target, right? So Vivado HLS is the best tool, I can tell you. It
Okay, okay.
depends on which target you want to use. But if you want to develop a ASIC chip, so you understand probably the difference between ASIC and FPGA, right? In FPGA is basically you are dumping your whole hardware into a reconfigurable architecture. And for that you need FPGA provider is say Altera or Xilinx, so you have to use their own HLS tool, right? So, and I have seen this Vivado HLS is quite popular. And if you try to say just to create a prototype, and this is basically create a prototype, right? You create a hardware, you put it into FPGA and you running in FPGA board, right? So for that you have to use, you can use Vivado HLS. But if you want to develop a chip or say IC, integrated circuits, right? Through ASIC flow. So in that case, you have to use general purpose HLS tool like Synopsys has their tool, Cadence has their tool, Mentor Graphics Catapult is very popular. So you can use that and they can generate a generic hardware, a generic Verilog, which is not FPGA target, right? So that you can actually take it through Synopsys Flow or Cadence Flow or Mentor Graphics Flow. And you can actually create a layout and which you can actually fabricate through some fabrication lab. And you get your chip which is dedicated for that particular application, right? It depends on your application, but usually in the academic purpose, we usually use Vivado HLS because we just want to give a proof of concept, right? So, but if you want to develop a dedicated chip for an application, you have to use Mentor Graphics Catapult or those kind of generic tools. Okay.
Okay. Sir, regarding the efficient designing of hardware efficient utilization of design flow, basically planning and verification logic synthesis, which is the if I will be choose Intel. So basically Intel as well as Intel Premium is a good source of basically that in a basically efficient C-based C coding efficient utilization of hardware. So if Intel in replace we use Mentor graphics or other tool, then it will be it will be provide same result as FPGA if we target any C hardware efficient FPGA prototype. I want to ask a question, sir.
Yeah, understood. Thank you. So yeah, so
Yeah.
if you ask me this question, and if my honest answer is like, see, if you want to map into Intel FPGA, now Altera is part of Intel, right? So for that you should use Altera HLS tool because they knows their FPGA architecture better, and they generate very log where they basically use those uh, component of the FPGA board directly through RTL, right? I can, for example, suppose you want to use the DSP, right? I have seen when we were to generate RTL, they instantiate the DSP directly, right? So this is the advantage of Vivado HLS. So to answer your question very specifically, that if you want to use Altera FPGA board, you use Altera's code, Altera's HLS tool. Uh, and then for if you are using FPGA board from Xilinx, you have to use Vivado HLS because that they knows better their FPGA and they generate RTL which is can be suitably mapped to those board, right? And and if you want to develop for integrated circuit, I mean not for FPGA target, you can use any commercial product. Specifically, I have seen that Mentor Graphics tool is very good. But one comment here is that this tool is basically not intelligent, right? Intelligent is you. The tool has lot of optimization opportunity. Only thing what you have to do, whether see if you just take any code and synthesize using Intel tool or Xilinx tool, you won't get a good result. I can guarantee you that. you have to apply the optimization judiciously, right? You probably sometimes modify the C code little bit so that it become harder efficient. So this has to be done. So other than that, these tools does not know any magic because they are not intelligent enough to understand which optimization to be applied where, right? What it does, it basically you instruct the tool that you apply loop optimization. It will not automatically apply loop optimization, say loop pipelining, right? So these things. Uh, so to generate an efficient hardware from a C code, irrespective of what tools, these all tools are very quite efficient in my opinion. They have a lot of optimization features, but whatever tool you are using, you need to know very well what are the optimization available in the tool and how to use them, right? Unless you know this, generated hardware won't be that efficient. Okay.
Sir, basically, flow planning, designing power planning and flow planning and data path, like as a ARM, basically ARM controller generation, data path ARM control generation. So basically, in that section, in that time, which type of tool will be best for, as a Intel or Synopsys? What is the difference between both will be tools? If you use RTL level optimizations in basically data path controller generation. So in data path control generation and allocation binding, then basically which tool is very helpful for generating the timing as well as the IO resources, as well as a good generation of power planes, IO planning, floor plan element. So core utilization reports. So which tool is best? I think if you choosing Intel as well or Synopsys.
I mean, the answer is same. Basically, see, in the high level synthesis, there is no floor planning, right? Floor planning is basically physical synthesis. So there is no relation with floor planning with the data path synthesis. So data path synthesis is basically it identify how many resources you need to execute that C code into hardware, right? And I can tell you all this tool has very good implementation. So these people are not fool. They have implement the best possible algorithm. But as I mentioned many times, it's basically you have to understand the optimization available in the tool. Otherwise, you won't be able to use the tool judiciously. Okay. Okay.
Regarding advanced dueling, basically advanced dueling will be used in C-based VLSI. Which process will be first to last process explains advanced dueling. Advanced dueling basically done in before that allocation scheduling or otherwise after allocation scheduling. Next question, advanced scheduling basically. Advanced scheduling is very popular.
Advanced scheduling.
Yes, yes.
See, there is no advanced scheduling in high-level synthesis. It's basically what scheduling strategy is implemented, and I can tell you because I worked in a commerce EDA2 company and I have implemented high-level synthesis tool there.
Okay.
Most of the company use list scheduling, right? So they use because the scheduling problem is NP complete. So whatever strategy you come out, you may not always guarantee to give a optimal solution in polynomial time, right? So what they do, they use very good heuristic and they use list scheduling. And I can guarantee all the tools use list scheduling in backend. So and they generate quite good schedule. So that's not the constant. I mean, it always generate a good hardware. Only thing you have to apply the optimizations properly. Okay.
Yes, sir. In digital signal processing, hardware efficient C-based VLSI coding, then this depends upon Synopsys. If we choose, then it will be the same result as well as if we choose Intel.
See, all the tools have the pragmas, right? So we apply optimization using pragmas. So these tools have their different pragmas, and there is no guarantee that this all the tool has the equivalent pragmas, right? So they interpret certain things in certain way, right? But the common things like say loop pipelining, loop unrolling, say array partitioning, these are all there in all tools with different name, right? So you need to just go through their user manual and you'll understand. Say data flow is another example. Data flow is there in every tool, I can tell you. But how exactly they apply, whether they prefer ping pong or FIFO, this is their internal detail and you have to go through the user manual. But in general, in high level, all the tool has all the very common optimizations available with different pragma. You have to understand those pragmas and you have to use them. Okay.
Yeah, yes, sir. Verilog Excel. If we choose a Verilog Excel model, then higher efficient which tool for Verilog Excel? If I choose a user guide Verilog Excel.
What is Verilog Excel?
Language Verilog Excel is the cadence, basically cadence permission user guide. Verilog Excel design systems.
That is what I'm telling you. Na? So it depends on which tool you are going to use. You need to understand their manual well. So I use Vivado HLS. So I know all the optimization available in Vivado HLS. I mean, see, this is commercial tool need a lot of money. So in academic, you may not have the availability of all the tools all the time. In industry, you may have, but in academics, these tools are not freely available, very honestly. I use Vivado HLS because that is available in my institute. And those I have seen it has all the optimizations that needed is available. Right. So I cannot comment on other tools, but Vivado HLS is quite good.
Yeah. Basically, sir, any restriction problem of hardware efficient generating report based upon that. Permissions and allocation such as data path generations, pipelining, controller generation. So any restrictions will be different tools. Something like any permissions type of restrictions.
Your permission is basically your if you buy the product, it is available with you. So there is nothing there, and you don't need to bother about much about the allocation binding this. It is automatically done. You must bother about this how to apply the optimizations. Okay. And permission is basically if you buy that product, you have you have all the optimization available. Otherwise, there is nothing, right? So there is no permission issue. But as I understand, you need to become master of the optimizations in HLS to use it efficiently.
Okay, sir.
Okay, I think I have answered your questions. Yeah. So
yes. Okay.
yeah. Okay. I think there is not much questions, so I'll wait for a couple of minutes and then I'll wind up this session. If there is any other questions, you can always ask me in the chat box. And if I do not get any questions in next 2 minutes, I'll close this session here.
Hello, sir.
Yes.
Hello. Yeah, sir.
Yeah,
Simulation-based verification. Simulation-based verification. Basically, need sir. Simulation-based verification is the same as RTL to C code reverse engineering process.
No.
Phase-wise verification.
Simulation-based verification means you are going to give and test case or input. You run the Verilog, you will get an output, and you know for that input what is the correct output, and you compare. So that's all. Okay.
Okay.
Let me finish. So once you do it in the RTL level, what you have to use? You have to use RTL simulator. Right? So what it does, it basically simulates your behavior clockwise. And what I have seen that this RTL simulators are very slow. And suppose you want to run the whole tool for say 1 lakh possible inputs, and every one inputs, the whole circuit will run for say 100 cycles. So it is basically 100 into 1 lakhs, right? 100 lakhs, so 1 crore clock cycles. So it takes a lot of time. That is what I have seen, and this is very well known also. So one solution that my research group has proposed that is from the Verilog, I can generate a C code by reverse engineering, and that is also cycle accurate. And if I simulate that, now I don't have to use the RTL simulator. Once you have a C code, I will use GCC, and C simulation is much faster than RTL simulation. And we have seen, I mean, we have shown in one of our research paper that if I use that C code that I can extract out from the Verilog, and if I use GCC as a simulator, then I can actually generate a simulator which is maybe 400 times faster than RTL simulator. This is one of the way, but it is not the only way to do this RTL simulation. Industry use RTL simulators like Model Sim and those tools. Okay.
So for hardware security, basically, what is the role of FPGA technology mapping FPGA technology mapping as well as in hardware security purpose and front-end optimizations in C-based VLSI. Then FPGA basically regarding that basically simulation based verification.
Tell you.
Yes, yes.
I can tell you.
Yes,
So what is security? So what is security in your program? So you basically
cryptography
yeah. So
security.
you so suppose one AES algorithm is running and you want to get the key back, right?
Yes,
So
yes.
once you generate this hardware, you might store those cryptographic data directly or indirectly, right? There may be some 10 analysis at the 10th flow or the dependency flow. You probably may not be storing the key, but you have used that key to compute something and that result is stored in some registers, right? So once you store those things, what happened, there are some side channel created. So maybe it actually impact the power or it may impact the timing of the design, right? So what happened, this hardware attacker, what it does, they just see that side channels and they try to get the data. So what this hardware security concept is that you still develop that chip, but there is no side channel. Okay. So this is a there is a huge research. It cannot be discussed in this 5 minutes forum, but if you're interested, you can actually go through it. This secure implementation of the AES and all, right? So there are a lot of technique like masking being applied.
Yes.
There are a lot of technique to stop glitch. So many
Yes,
things
sir.
are there. It's a complete domain of research.
Lithography and etching purpose also used, sir, for that.
Yeah, so these are so there are
Regarding
many
that
ways you can actually get those information.
encryption and decryption and generation
Those are there, but hardware implementation without information leakage is a challenging task, and there are a lot of research going on.
But some main thing is the FPGA technology mapping, introducing FPGA for logic synthesis for circuit optimization. Sir, which is the basic criteria of security, hardware security in C code?
So that C code, I mean, what I'll tell you that what I do here is a little bit different. Is basically IP piracy. Okay, so this is not applicable to this kind of hardware security that I discussed. That you implement AES and it's leaking some information. Rather, what I do is a little bit different. What I do is basically you. So if you now think about little bit about this, how this whole process going on. It is specifically not for FP target, but for ASIC. So you develop your chip and now you have to fabricate. Once you try to fabricate it, you have to give your layout to third party because the fabrication lab is very costly. So you give your layout, which is your intellectual property, and in the layout, there may be some dishonest employee. They can reverse engineer and get the IP, and they can sell it in the market, right? They can build another chip and sell it into the market. So to stop this, what I usually do, there is another trend of research is basically is called logic locking. So you lock your design with the extra key. So what is going to happen? Even you create the layout, you give it to the fabrication lab, they can reverse engineer, but I'm not going to give the key to them. So even if they have the IP, they can't use it because they don't have the correct key, and the circuit will work only for a one correct key. Okay, so so what will happen? This actually is another domain of hardware security research where you stop this IP piracy, and you probably heard the terminology IP piracy, IP overbuilding. So this is a different domain of research and in context of the side channel. But in the course that I have taught about is a technique where I want to high level synthesis tool to generate an RTL which is already locked. So that even if this RTL I give you, you cannot use it because you don't have the correct key with you. Okay. So this is another domain of hardware security research. You don't club these together. Okay. But this is another domain where this side channel analysis based attacks are is another domain. But these two are different domain. The things that I have covered in the course is the security against IP piracy and all. Okay. Okay, I hope it answers your questions, Pratik.
Sir, last question, sir. Sir, one question last. Sir, phase-wise verification and RTL verification is both simulation-based verification is different. Yeah, both are same.
Different thing. So what I did is basically see simulation-based verification is you give some input, you run your design, and you get the output, and you compare whether your output is equivalent to the correct output.
Yes,
right? This is simulation.
Yes.
And this phase-wise verification or end-to-end verification, whatever I have discussed in the course, is formal verification, where I'm not going to use any input. Okay, I'm going to formally prove that my Verilog code is functionally equivalent to the C code. Okay, So this is formal verification tool, and which is completely different from simulation verification tool. The problem with simulation that in the simulation you cannot cover all possible input. There are too many inputs, right? So only so that simulator does not guarantee 100% correctness. But usually, if there is an obvious bug, you will get it. But formal verification, if it says something is equivalent, it get 100% guarantee of the correctness. So that's why this formal verification is much complex problem. And there are a lot of research going on this formal verification for C2RTL. Okay, but simulation is a very shortcut technique to give some confidence. Most likely my generated code is correct because I have run for 1 lakh inputs and it's giving correct output. There may be some corner bug which may not be covered by this simulation, for which you should check the formal verification. Okay.
Okay.
Okay, thank you, Pratik. So with this, I conclude this session.
Thank you so much.
Thank you again for joining this. Okay.